So this is chapter 9, the beginning, and chapter 9 is all about inferences from two samples. So now instead of having an old idea and then a new idea that we're testing against it, now we're talking basically about two ideas and how they compare to each other. So the big difference between chapter 8 and chapter 9 is that chapter 8 is one sample and chapter 9 is two samples. So that's really the main difference between the two chapters. Now, section 9.1 is on two proportions. So we're still doing hypothesis testing. We are still creating a null and alternative, doing a test statistic, finding a p-value. All of that stuff is the same. We just now have two samples instead of one. So let's look at about a scenario. Think about whether you plan to vote in the next presidential election in 2020. Coming up. Let's say I split the responses into two groups, females and males. So we find out what proportion of females plan to vote in the election and what proportion of males plan to vote in the election. Okay. And let's just say we have, 100 people that are surveyed randomly, and maybe we find that for women, 55 out of 100 plan to vote, and let's say for men it's 45 out of 100. Now you might look at that and say, well, we can just tell from looking at those numbers that less men plan on voting. However, doing the hypothesis test allows you to determine whether the difference between the two proportions is statistically significant. So it's not really about what the proportions actually are. What we care about is, are they the same or not? And what you might be thinking is, well, they're obviously not the same. But again, the difference, it still might be too close to tell, dependent on the sample size, similar things like we saw in chapter 8. Now, chapter 9 is one of the most important, chapter 9 is an important chapter, and section 9.1 could be considered the most important section in the book. And that is because this type of hypothesis testing has been done many times and has led to the reason that we have things like the polio vaccine. So back in the 1950s, a vaccine was developed for polio and they had to test it out. And so what they did was they gave 200,000 children the vaccine, and they gave 200,000 children a placebo, meaning they gave them nothing but didn't tell them that they were receiving nothing. Then they looked over time to see how many of the children developed polio. Now, it was only 33 out of 200,000 when they got the vaccine. It was 115 that got the placebo and got it out of 200,000. And again, those numbers are very, very small. I mean, we're talking about 0.000 something in terms of the proportion. But it was still enough to show that the vaccine had an effect. And it's the reason that we have the polio vaccine today. Nowadays, testing on children would be incredibly rare. For something like the vaccine trials that they're doing for the coronavirus, they are doing those on people that are volunteering, basically. So it might not be as random of a sample. I'm sure they're trying to randomize it, but the people are choosing to do that or not. Okay, so it's really important because you're comparing proportions, and that's significant. So in this section, 9.1, we will deal with independent samples, and we're going to have qualitative variables. So for example, like in this above example, the variable is whether you plan to vote or not. And the answer to that would be yes or no. So that's why it's qualitative. All right, so let's think about our beginning of this. So the null hypothesis is always going to be, are the proportions equal? Now, if the proportions are equal, then their difference is 0. So just moving the p sub 2. So we have p sub 1, p sub 2. Moving the p sub 2 to the other side, you have p sub 1 minus p sub 2 equals 0. So first, we collect sample proportions. So we collect sample data, and that will give us proportions. Okay, so we're talking about, from that's going to give us P1 hat and P2 hat. So we're still trying to infer something about the population proportion based on these samples. And then we see if the difference in the sample proportions is anywhere close to 0. So let's remind ourselves. Let's say, for example, we have a null hypothesis, which is always going to be the case, of that P1 equals P2. Let's say our alternative is that P1 is less than P2. Okay, that's what we're trying to see if we have enough evidence to support. So if we test some sample data, and our sample data says, well, the sample data shows that P1 hat is equal to P2 hat, well, that definitely is not enough evidence to support the alternative. If P1 hat is only a little bit less than P2 hat, and again, little is subjective, it's based on things like alpha, how strong your data is, it may not be enough to support. So fail to reject. So notice these are still the same decisions. These decisions are no different than chapter 8. Now, if you have P1 hat greater than P2 hat, you might be saying, well, why did we even create an alternative for less than? This would be a very atypical type of test to do because it completely goes against what you're trying to show. So in this case, we'd also fail to reject. But again, that would be super uncommon. And this is really the key thing that we want to have happen. We want to have enough evidence to say, oh yes, here's our sample evidence, and look, P1 hat is really less than P2 hat. So we have this significant, sufficient evidence to support the alternative. So in that case, we could reject H naught. So that's really the only situation where that's going to happen. So just typical things here, we're talking about proportions. So we want samples that are simple random samples, and one of the key things, this comes back up in section 9.3, is that you want the samples to be independent. So that just means I have a survey of males over here and I have a survey of females over here, and they're not linked in any way. We need to have at least 5 successes and 5 failures. This is something we've seen before in earlier chapters, even in chapter 7, with just the fact that you need to have a large enough amount of successes and failures. Success might be like you're voting in the next election, or you're not voting in the next election. You still need to have enough of those occurring so that the distribution looks normal, so that you can use the Z table, the Z normal distribution. All right, so here's our different hypotheses. We've got either, so notice same thing here and here and here, that P1 is equal to P2, and then just 3 different possibilities, again, very similar to what we did in chapter 8, that P1 is not equal to P2, that P1 is less than P2, or that P1 is greater than P2. And those are all the things that we'll see. Level of significance, if it's not given, we will be using 0.05 just to be safe, right in the middle. Remember that that choice depends on the seriousness of making the type 1 error, because significance is alpha, and that's what alpha represents. So down at the bottom here, once we've checked that we have the requirements, we've done our hypotheses, we look at what our level of significance is, then we're ready for the test statistic. Now, one thing I want to mention, these test statistics are big, so I totally get it. It's a lot more than chapter 8 because you're comparing 2 proportions against each other. So one thing you want to write down is that based on our null hypothesis, P1 is equal to P2. That's the null hypothesis, and so that's always going to be 0, so it doesn't need to be written. So your focus is just on what is the difference between our sample proportions, and then divided by this square root of some crazy stuff. It's not so crazy, it's just your 2 sample sizes for the proportions. They don't have to be the same. And then this is what is called P-bar. And it's the idea of pooling, P-O-O-L-I-N-G, the data together. And again, it's part of the test statistic. It is not something we made up, but it's some very intelligent statistician who determined that this is what is needed. And so you can see it's just combining the two proportions and, you know, adding the two numerators together of the proportion, dividing that by the addition of the two denominators, you know, your sample sizes. And not surprisingly, your Q hat is just 1 minus your P, your Q bar is just 1 minus your P bar. So that's all that is. All right, we're almost ready for an example. The last thing I'm going to mention is, of course, we are using the p-value method in my class, so I'm not going to focus on the critical value method. Mine will only be the p-value for me. And here is what you should probably be remembering, which is just, here is our left-tailed test, here is our two-tailed test, and here is our right-tailed test. So very, very similar to the Chapter 8 stuff. And it's still the same idea. We want a low p-value. We want that to be less than our significance level. That tells us that our evidence is strong. And in the middle here, or down at the bottom, we write our conclusion, where we're either going to reject or fail to reject the null. So let's take a look at an example, and it'll all come together. An insurance company is concerned that men are more likely to speed than women. Do you think that's true? In a sample of 500 randomly selected women, 27 have been ticketed for speeding in the last year. In a sample of 250 randomly selected men, 26 have been ticketed for speeding in the last year. Use a 0.05 significance level to test the insurance company's claim that the percentage of women ticketed for speeding is less than the percentage of men. So this is a very likely scenario because insurance companies have to decide how much they're going to charge men and women, people of different ages, because they're going to base it on how likely that group is to get, you know, into accidents and tickets and things like that. So it's very, very likely that they could be doing stuff like this to determine that. So a really good thing, even more than in Chapter 8, is to put your sample evidence, because you have two sets of data here, two sets of sample evidence. And so for women, I'll call that X1, N1, and then that will give me my P1 hat. And then for men, I'll have X2, N2, and therefore P2 hat. So if you want, you can take a minute, pause it, make sure you can get all this data down. Okay, so that's everything. This is our sample evidence, we'll also need for the test statistic p-bar. And p-bar is simply, it's the idea of pooled data. So I'm going to take my numerators, add them together, divide them by my denominators added together. Now that's going to give me 53 over 750. And then of course our q-bar is just 1 minus 53 over 750, which, you know, if you're doing it, is 697 over 750. It is likely that I will let you use your calculator on the test statistic when we talk about that stuff, but we will do a first example just to show you. So let's come up with our null and alternative. One thing to notice with these problems in 9.1 and 9.2 is that we will not have numbers in our null and alternative, no numbers, because you're saying is P1 equal to P2, or in this case, notice that it says percentage of women ticketed for speeding is less than. So that's telling us our sign that we need. P1 is less than P2. Okay, so no numbers there because we're just comparing the two proportions. So now we will get our test statistic. It is a Z statistic because we're talking about proportions here. So we're using the idea of the normal distribution. So notice what this is, and you can come up with these as decimals, that's fine. I happen to have them in my notes as fractions, so I'm just going to write them as fractions, and then if you want, you can put them as decimals. But we have our P1, 7, that looked like a 7, 27 over 500 minus 26 over 250. So it's really just what is the difference in the two proportions. We're trying to figure out how close that difference is to 0. And the closer that is to 0, the closer your z star is going to be to 0 as well, which is, putting it in the middle of the normal distribution, which is not a small p-value. So now in the denominator, you'd have to go back on the last page to see what the test statistic is. But notice it is p bar q bar divided by n1. So it would look like this as fractions. P bar times q bar. I'd probably write this a little bit smaller, but I have the tablet, so divided by n1, and then add to that, so I'm going to need to extend this very long here. Then I have another p bar, and you honestly could put this all into your calculator at once. You could use your fraction bars, and this is 697, oh, that would have made a difference, divided by 750 all over n2, so 250. So yes, it is big and it is huge, but you could arguably put it in your calculator at once. It would just be a lot of work. And if you do that, you should get, you can try it if you want, negative 2.52 as your test statistic. Now this makes sense because you're checking that P1 is less than P2. So that's sending you over into the left-hand side of the normal distribution. So this is, again, a measure of how strong it is, how strong your sample data is here. And again, because you're being sent way away from the middle, that's going to be a smaller p-value. So this is still the normal distribution. So we have 0 here, -1, -2. And so a negative 2.52, like probably over here somewhere, and there's some little bit of area here, that is your p-value. That is the probability that if the null hypothesis was true, that you would get data as strong or stronger than the data that you got. So what we can do is our p-value is just the area to the left of that z star equaling negative 2.52. So what we could do is we could take a look in the tables. I know a lot of you are big fans of the normal, and you can use normal CDF on this, that's okay, so you can get the same thing. But I'm going to look in my tables, I'm going to look for a negative 2.5, and then I'm going to go over to 2, and that gives me 0.0059. So my p-value is 0.0059. Notice that is very, very small. It's a very, very small number. Our alpha here was given to us as 0.05. And we can see just by looking at that our p-value is smaller than our alpha. And, because remember, alpha is the significance level. And so that's it. I mean, it's the same determination. We can see from this, the decision about the null hypothesis is to reject H0. The P is low, the null must go. We're going to reject the null. So our conclusion, very similar to chapter 8, just thinking about what our claim is. If we go back here to the beginning, notice that we are given some information about our claim. The company's claim is that the percentage of women ticketed for speeding is less than, so our claim is the alternative. So that does affect our sentence just a little bit. And now we can write it. So because we rejected H0, there is sufficient sample evidence to support the claim, or you could say support the insurance company's claim, that the percentage of women ticketed for speeding is less than the percentage of men. So just to bring it back, we just saw a bunch of this in chapter 8, but just a reminder, because we rejected H0, there is sufficient sample evidence, and we're going to support the claim because our claim is the alternative. So again, this is totally likely that you'd have an insurance company that would use this type of data to then charge men more money for their insurance on their cars, because they would say that the data supports that they're more likely to speed and get tickets, which of course costs the insurance companies money.